uma categoria triangular. Eu tinha dois morfismos, F e G, então eu queria, e esse era um triângulo distinguido. Then, eu queria provar que esse cara era zero. E eu simplesmente estava usando as zetas no sentido contrário. A gente sempre tem esse triângulo distinguido. Esse era o axioma TR1. Aqui eu tenho a identidade. E a gente tem esse outro triângulo distinguido. Então aqui eu coloco a identidade. Aqui tenho F, esse diagrama claramente comuta. Aqui eu tenho a identidade. Esse mapa é zero, é o único mapa que posso ter. Então esse mapa aqui comuta, esse mapa aqui comuta. E esse é o único mapa possível aqui é o zero, simplesmente porque esse objeto é o zero. E por TR3, esse é o morfismo de triângulos distinguidos. Mas então, se tudo comuta, o mapa de A para C, nessa direção, é a composição de F com G. E nesse sentido é zero. Então, essa é essa identidade. Eu estava tentando fazer, obtendo um mapa daqui, eu queria fazer as setas nessa direção, que claramente eu nunca ia funcionar. Acho que depois de 1h30, a pessoa fica cansada. Ok. Eu estava dando os axiomas de uma categoria triangular. Deixem-me não finalizar. Eu quero dar... Está faltando um axioma mais. Tá? Lembrem que TR1 era a existência de S. Este cara é distinguido e para todo morfismo existe esse cara aqui, não é único. Então, que esse cara é distinguido. TR2 era que se eu tenho um distinguido, vamos fazer rápido agora. Se somente sim, esse triângulo é distinguido. Tá, se aqui eu tenho F, G e H, então aqui eu tenho G, H, e aqui eu tenho menos F shifted por 1. E esse é and this is an if and only if, and tier 3 was this, that if I have two triangles that are distinguished, and a map between them. Well, not a map between them, I'm sorry. But you have maps here, and maps here, making this diagram commute. Then this exists, making it into a map of triangles, and distinguished triangles. So we're missing one axiom. And recall that we wanted to have, or something that looks like was going to happen, is to look at the category of cochains on cochain complexes or chain complexes on modules over a ring. And distinguished triangles seem to be something related with the cone, or short exact sequences of complexes of modules. It wasn't exactly the same. We checked that we couldn't have that, but at least it looked like closely related to short exact sequences. So let's look what could happen if we had short exact sequences of complexes. So if I have, say, A into B, C, a short exact sequence of complex. So let's imagine that I have 0 and 0 here. And these are just complexes of modules over a ring. And I have another one. So I can think that A is inside of B. Let me say this in a different way. Okay. How am I going to make this the least confusing? So let's change names for these things. So what I want to look at is the situation where I have three modules, say A inside of B, which is inside of C. And I could take C divided by A. I could take B divided by A. I could take C divided by B. And these are our modules. And what you have for free is that, well, you see, if you look at C divided by A, you can mod out by B divided by A, and this is isomorphic to C divided by B. That's just simply, the usual map is that B is inside of C, and A sits inside of A here, so it maps to 0 here, so you can look at this quotient, and this gives you a natural isomorphism between these two. So how does this look from the point of view of like the corresponding short exact sequences of modules? So what you have is this guy looks like the short exact sequence is C divided by A. Let me write it here. Is that you have C divided by A, I'm sorry, B divided by A inside of C divided by A, which is surjects to C divided by B. And imagine the zeros and the 0 on both sides. Imagine 0 like 0. But now this guy itself is a co-kernel. This is the co-kernel of this inclusion of A by B. And this guy itself is a co-kernel. Oops, I think I might have screwed up exactly the opposite way. So this is, God damn it. C goes here, A goes here, 0 goes here. We're drawing this. And this itself is a co-kernel, where C maps there, and B goes here. 0 goes here. And, well, so now this is just the inclusion, this is the identity, this is the identity, and this is the inclusion. And this is just the inclusion as well. So you have these diagrams like this. Okay, so now translate this to a a triangular category. And the statement we're seeing here is that if we have two exact triangles, two distinguished triangles, then there's a third one. And I don't want to write it, because I'm sure I'm going to make a mistake, but let's try to write it. So if I have two distinguished triangles, so these are going to be this and this, for example, then I'm going to claim that there exists a third one and that it fits in a diagram that looks like this. But that's essentially the same thing that were done for modules. If I have three modules, or if I have, so if I have three modules, you can put them with inclusions like this, you can put them in a diagram like this. So let's suppose that you have two distinguished triangles, and these distinguished triangles are going to be looking like those. So, but perhaps I need different names now. So I'm going to have, well, it doesn't matter. I'm going to use these names. A into B into C. A shifted by 1. So this C here wants to look like the quotient of A by B. Let me shift this everything below. A, B, C. A shifted by 1. And I have another one that looks like A. So this C is completely different now. Let's take a different one. Into C. This is D. Perhaps I'll use B prime. And then C prime here. A shifted by 1. This A is important that it's the same as this A, so that this is the identity map, and this is the identity map here. And then now this B here is the same as this B here. But this guy here was the same as this guy here, and that I do want to keep. So I'm going to keep this B here, this B here. No, this is not here. But this C here was the same as this C here, so that I do want to keep. So this is the identity, and this map here is the same as this map here. So let's start putting names. If this is F, this is F. And this is going to be C second prime. And this is B1. This is not equal. This is this map shifted by 1. So if this is G shifted by 1. And this is exact. This is distinguished. Okay. And no, this is C prime. And this is the identity. So everything is, shoot, no, I'm sorry. This was C prime. This was C double prime. And this is the one that exists. Okay, so let's check what are the conditions here. So the whole point was that this guy existed and this sequence was exact. So the same thing happens here. So I'm telling you, this is a distinguished triangle. This is a distinguished triangle. Then there exists this distinguished triangle. And this guy is distinguished. This is the condition. This is distinguished. Given that these two guys are distinguished, and this is the identity map, and then this guy is distinguished fitting in this diagram, where this arrow here is the same as this arrow here, which is the same as this arrow here, which is part of your data. This F is part of your data, which is equal to this guy here, which is part of your data, and well, and everything is exact. So these arrows here are distinguished triangles. So that's the last axiom, and we're never going to use it, so it's not so important. I think we're never going to use it. But yeah, so let's keep it. If I have time by the end of the lecture, I'll draw it properly with an octahedron. This is called the octahedron axiom. Okay. Right. So what I call here C, C prime, and C double prime are these three guys, B over A, C over A, which is B prime over A in this case, and B prime over B, which is C over B in this case. Okay, so now let's prove something. So we've checked that the composition of two guys is 0, which is the brain dead thing that I was trying to do by the end of the last lecture. So let's see something else that is implied by that. So lemma. Let's suppose that you have an exact triangle. I keep calling them exact triangle, but it's just a distinguished triangle. A, B, C. A shifted by 1. So then pick any object in your category. Say D is an object in your category. And let's look at homes. D, A, home, D, B, and home, D, C is exact. Here, these maps are just the compositions with these guys, with F and with G. So this sequence is exact. Let's prove that. Okay. So let's look at something that is in the kernel of this map. I cannot talk about kernels in the category C. C is a triangulated category, so it doesn't make any sense to talk about kernels, at least not in general. But here, these are just vector spaces. So let's look at a morphism from D to B that maps to 0 when I map to C. So let's look at some guy here that maps to 0 here. So what is this map that I obtain from D to C? Well, it's just the composition by G. So this is G composed with phi, and this is 0. Then I claim that this comes from a morphism from D to A. Okay? So what we want is a morphism from D to A, and what I have is a morphism from D to B. Here's my F. And when I compose this this is my phi, and when I compose this morphism with this G, I get 0. This composition here is 0. So that composition is the same as this composition. I can take this to be the identity, and now I can complete this to a distinguished triangle. And here was my original distinguished triangle. So here I can just, the question here is, does this arrow exist or not? Okay. So now here, this one exists because this is the only map that I have is from 0 to C. And the question is, knowing that I have this phi, what is the condition? That phi goes to 0 here. So that means that this is the same as this. So now I know that this diagram commutes everywhere, except that I do not know if these arrows exist. But now let's look at TR3 in conjunction with TR2. So TR3 says that whenever you have two distinguished triangles, and you have two of the three arrows, well, it says explicitly if I have these two arrows, then the third one exists. But because of TR2, these diagrams here is the same thing as if I took B to C to A shifted by 1 to B shifted by 1. So this is distinguished if and only if this is distinguished. And the same thing here. This is distinguished if and only if this guy is distinguished. And now, if I have these two arrows, that's the same thing as having this arrow here, just shifted by 1. So if you call this guy F, just shift that guy by 1. And the same thing here. So if you had this arrow here, then now you have this arrow here. And that's this arrow here. And so if you have the first and the third arrow, this guy exists. And if you just circle again once more, you're going to check that if you have the first arrow, if you have the second arrow and the third arrow, then the first one exists. And this one is always forced to be the first one shifted by 1. So if I circle this one once more, I'm going to check exactly this condition. If I have two distinguished triangles, this is distinguished by TR1, this is distinguished by a supposition, and I have two of the arrows, of the three possible arrows, then the third one exists. So this says that this guy exists, making this diagram commute, and if this diagram commute, it means that the composition this way is equal to the composition this way, which is phi. So on this side, I have phi, and on this side, I have the composition of this map, whatever I call it, xi, with f. So xi is here, and it maps to phi here. So that sequence is exact. And of course, the same way with the arrows in the other direction, you can look at the other functor, which is contravariant. So if I have an exact triangle, A, B, C, to A shifted by 1, and I hit it with hom into D, so if I hit it with hom into D, well, then I have this, and I have hom B into D, and I have hom C into D, and this guy is exact. Same proof. Just that instead of starting from D, from this guy and trying to map it to this distinguished triangle, you start with this distinguished triangle and try to map it to this distinguished triangle. But now by TR2, so as a corollary of this, which is just application of TR2, you get that hom, we just checked that hom GA, hom DB, hom DC was exact at this point. But then again, the triangle B to C to A shifted by 1 to B shifted by 1 is exact. So the map hom DB to hom DC to hom DA shifted by 1 is exact at this point. And then again, using TR2 again, to hom D B shifted by 1 and to hom, etc. is exact. So you get a long exact sequence, and actually this comes also from hom D C shifted by -1. Shift was an equivalence, so it has an inverse. So you get a long exact sequence of vector spaces for any distinguished triangle. Okay. Okay, so yeah, I want to prove just elementary stuff about triangular categories now. The next step is I'm going to be looking at the following statement. Let's look at okay. So let's look at a triangle like this, which is distinguished. And let's suppose that F now is an isomorphism. F is an isomorphism between A and B. So this F here is an isomorphism. So here I have my G, and here I have, let's say, H. Okay, so if F is an isomorphism, then what you could do is here use F inverse to map it to A. And again, the composition of F with F inverse is the same thing as just the identity map. So I can use the identity map here and the identity map here. And that diagram commutes. Now, we have always this distinguished triangle. And this is the identity map. And everything there commutes. So what you get is that this is a map of triangles. And now let's go the other way around. Let's map this to A by the identity map. Again, now let's map it by F to B, which is an isomorphism. And then from A to B, you just have F. And now this diagram commutes. Now, from F, from B to C, you have G here. And now I need to check that this diagram commutes. But this direction is F composed with G. And this direction is 0, because it's the only possible map that I have from 0 to C. But we've checked that this composition is 0. So this does commute. On the other hand, I have this triangle here and this triangle here, and I've got this, which is an isomorphism. Oh, I'm sorry. These two are distinguished triangles. The three arrows are distinguished triangles here. And this composition here is the identity, which is an isomorphism. This composition here is the identity, which is an isomorphism. This composition here is the identity, which is an isomorphism. I claim that, therefore, this composition here is the identity. Well, I claim that it's an isomorphism. Okay, so claim. Claim. If I have two distinguished triangles, well, and I have A prime, B prime, C prime to A prime shifted by 1, and I have a map of triangles. So I have these arrows. This guy is forced to be this guy shifted by 1, so this is F shifted by 1. This is F, G, and H. I'm using the same letters for different kind of maps, but it doesn't matter. So the claim is that if two of these three arrows are isomorphism, then the third one is also an isomorphism. So the claim is if two of F, G, and H are isomorphisms, so is the third. If we were in abelian categories, this would be simple. But we're not. But let's see how the claim implies something interesting here. So I started with any distinguished triangle here, and the only condition was that F was an isomorphism. And what I've gotten is a map from this distinguished triangle to this distinguished triangle, which has this as an isomorphism, this as an isomorphism because it's the identity, and this one is the identity, which is this guy shifted. So this implies that this composition here is an isomorphism, but it's a 0 map. So this implies that C is isomorphic to 0. Conversely, if C was isomorphic to 0, then you choose this guy to be an isomorphism, and you're going to check that F is an isomorphism. So conversely, applying TR3, you get that C is isomorphic to 0 if, well, implies that F is an isomorphism. How? Again, if this is an isomorphism, this is the identity, this is the identity. Now we have two distinguished triangles and a map where I have the first and the third arrow. This guy is always shifted of this. Then TR3 tells me that this arrow here exists. And now the fact that this diagram commutes says that this arrow has to be the inverse of that F here. So actually what we're proving is that there exists some F inverse. So in the distinguished triangle, one of the arrows is an isomorphism if and only if the third guy is isomorphic to 0. Which again is the same kind of things that we have been seeing, that if we wanted to put some sort of triangular structure on the category of modules over, or cochain complexes of modules over a ring, then quotients somehow need to be isomorphic to 0. I'm sorry. Cones somehow need to be, cones of isomorphism somehow need to be isomorphic to 0. Yeah, so that's the condition we already had last lecture. Okay, so this follows from this claim. So let's prove the claim. Okay, so I need to prove that if I have two arrows that are isomorphic, then well, so is the third. Okay, so how are we going to do this? Well, let's suppose that I have two of these guys are isomorphisms. So I would like to check that, say that F and G are isomorphic. I would like to check that this H is an isomorphism between C and C prime. But now checking that I have an isomorphism between C and C prime, what I can do is always, well, probably for B it's going to be easier, it doesn't matter. But what I can always do is pick a new object D in my category C, and let's look at homs. So we've checked that this sequence was exact. So this we've already checked. Actually, this is not going to fit here. So let's do it like this. Hom A, I'm sorry, DA to hom DB to hom DC. This was exact at B, at this point. And the same thing for hom DA prime, hom DB prime, and hom DC prime. So this was also exact at the middle. Now, A is isomorphic to A prime. So this composition by F gives you an isomorphism between this and this. So this is an isomorphism. And now this is an isomorphism of vector spaces. The same thing here. Composition by H is an isomorphism. Induces an isomorphism here. Okay? So here I am supposing that F and H are isomorphisms. So if F and H are isomorphism, then this guy and this guy are isomorphic, then this and this is an isomorphism. And then composition by G is this map here that I do not know if it's an isomorphism or not. But now I am on vector spaces, and I just checked that I have an actual long exact sequence. So I also have hom DA1 here, and I have here hom DA prime 1, and this is also an isomorphism because it's just the same as this isomorphism shifted by 1 essentially. And same here, hom C shifted by -1 into here, and this is an isomorphism, hom D C shifted by -1. And now I have 5 columns of vector spaces where these two are isomorphic, these two are isomorphic, therefore this guy is isomorphic. Implies that this is an isomorphism. And this holds for every B, and obviously this is functorial in D. So this holds for every D in my category, and this is functorial. This means that the functor hom dot B is isomorphic to the functor hom dot B prime, But if these functors are isomorphic, that means that B is isomorphic to B prime because that was the Ioneda's lemma. By Ioneda. And that's sort of like game we're going to be playing all the time. All right. So the claim was that if I had two of these guys that were isomorphic, the third one was an isomorphism, and I did it for this and this. But now by TR2, any combination works. So okay, so we proved this claim here as well. Okay. All right, so once we know this, notice the following statement too, that I claim that if the map, so let's take again, a distinguished triangle, this is F, this is G, and this is H, and I claim that if H is equal to 0, then this sequence is, this triangle is split. So let me say what split means. If H is equal to 0, then there exists a splitting from C to B, which is a splitting of G. Namely, it's a right inverse to the map G. And moreover, B is the direct sum of A with C. My category C was not abelian, but it was an additive category. And this is an if and only if. Well, not really. Okay, so let's prove this statement. So if this map is 0 in a distinguished triangle, then this I have that B is isomorphic to the direct sum of these two, which is something we've used in the case of complexes. If the connecting homomorphism in homology was 0, then we've obtained isomorphisms between the homology of the guy in the middle as a direct sum of this homology of these two guys. We've used this all the time when we were analyzing next groups. Okay, so let's first construct this map. So what I claimed is that there was a map from C to B. So I want to construct this sigma, which is a splitting of G. So what does it mean to have a splitting of G? It means that I need a sigma that is in hom from C to B, such that sigma composed with G is equal to the identity of C. But this kind of looks like the following situation. I am looking at hom CB. This is where I want to construct something. And I have hom CC, which is where I know I have something, which is the identity of C. And this map is the canonical map, is the composition by G. So I'm looking for sigma here that maps to the identity here. But we have an exact sequence. That is hom C A1. And here is the composition by H. And this map is 0 because H is 0. And this was exact. So since this guy has to map to 0 here because H is 0, this sigma exists here. Okay? Since this sequence is exact for any triangle, for any distinguished triangle, and composition by H is 0, it means that this map here is 0. Therefore, this map here is surjective, and for any map here, I can pick a preimage. In particular, for the identity map, I can pick a preimage. Okay, so we have this map, sigma, from C to B that splits G. So now once you have that map, then of course you have a map. So now I have a map from A to B, which is just the inclusion, and I have a map from C to B, which is that sigma. So I can look at the sum of these two guys, and I get a map from B. Well, I get a map from the direct sum to B. I get a map from A plus C to B. So if I call this A and I call this C, I send this to f of A plus sigma of C. And I claim that this is an isomorphism. So let me call this guy phi. I claim that phi okay. So well, again, so if I want to find an isomorphism between these guys, then what I need to do is look at hom from any object into those guys. So I can look at hom from any D into the direct sum, and hom from any D into B. So I can look at hom into this direct sum, or I can look at hom D into B and check that these are naturally isomorphic. But I'm kind of stupid, and I have those diagrams already. So the fact that I had a triangle, that this A, B, C, A shifted by 1 was a distinguished triangle, told me that hom dA to hom dB to hom dC was exact. On the other hand, on vector spaces, I have this dA plus C, and I have hom dC. This guy is exact, and I have this map. Actually, I have this map. And this is an isomorphism, this is the identity, this is the identity. Continue it by the same argument as before, and again, I have this map, I have this is an isomorphism, this is an isomorphism, and the continuation of these two guys are an isomorphism. Here, I'm going to put this identity shifted by 1, and here I'm going to put this guy shifted by -1, therefore this is an isomorphism. And this holds for every D, so by Ioneta again, this implies that B is isomorphic to A plus C. So in triangulated categories, if any morphism in a distinguished triangle, if any of these maps is 0, then the other one is a direct sum of the other two. So one of the three objects is a direct sum of the other two. So that claim shifted by 1, applied TR2 shifted or cycled as many times as you need. Okay. All right, so let's start to move to more geometric objects. I mean, the whole point so far is that if you give me a triangulated category, then you get these exact sequences of hom, these long exact sequences by applying hom. And so the idea is to construct interesting triangulated categories such that the hom spaces are natural. the canonical example we're going to have is going to be shifts of modules on a variety, and then these home spaces are going to be sections. So the question is, how do you construct a triangulated category out of just sheaf of vector spaces or sheaf of O modules on a space? All right, so but before that, we need to talk about the equivalences and exact functors. So now let's suppose that you have two categories, and a functor between them, and these are triangulated categories. So if I only view them as additive categories, a functor is just an additive functor. Okay, but I would want to have this functor to be compatible with the triangulated structure on these two categories. So an additive functor is called exact and now there's no left or right exact, it's just exact if, well, two things. First of all, it needs to commute with translation on both categories. So this means that for every, well, it means this. One thing you could do is translate on the category C, use the translation in C. This is an equivalence from C to C, and then you apply F to go to D. Or, so that's, this thing is a functor from C to D. Or you could do F first and compose with the translation on D. So this is another functor from C to D. And I have two functors from C to D. I can ask them to be in isomorphic. So that's the first condition. Let's read what this is. So if you have an isomorphism, this means a natural transformation from this functor to this functor. What is a natural transformation? These are functors from C to D. So that means that for every object A, an object of C, what we want is a map from this applied to A. What is that? Well, T applied to A, we denoted it A shifted by 1. And then I have F of this. So that's an object in D. On the other hand, I could take F of A, which is an object in D, and now translate it. And what I want is a map from this object to this object, and I want it to be an isomorphism. Okay, so I need natural isomorphisms for every A, and I'm going to fix them, and I'm going to use these isomorphisms to identify these two objects. So in particular, this implies that I can identify FAN with F of AN, and I will do so, so I'm not going to be writing parentheses anywhere. For every A and every N, an integer. Okay. Since we can do this, we fix this isomorphism. There could be many such isomorphisms. Just fix one, and you identify these two objects by that one that you fixed. So that's one condition, that your functor needs to commute with the translation. But then the other condition is that it sends distinguished triangles to distinguished triangles. So I would want that that if you have A, B, C, and A inverse, A shifted by 1, distinguished in C, then F of A to F of B to F of C to F of A shifted by 1 is distinguished. And notice that we actually need that first condition first to even make sense of this. Because if this guy was F, then this guy is F of F. This guy is G, this is F of G. If this is H, well, this is F of H, but F of H doesn't really land here. It lands on F of A shifted by 1, which I can identify via that isomorphism there. So I'm requiring that this is a distinguished triangle in T. So that's what an exact functor is. And the only lemma that we want to prove today is that adjoints of exact functors are exact. Which is kind of something that we've done. So the theorem for today is that adjoints of exact functors are exact. So if you have a functor between triangulated categories and it admits a right adjoint or a left adjoint, both of them, if f is exact, then both adjoints are exact, if they exist. Okay, so that's a theorem we want to prove. And before doing so, let's play a little bit with what we have for adjoints in general. So recall, if I have two functors between two arbitrary categories, now not necessarily, well, I need them to be k-linear because I want my vector spaces to be vector spaces, not just sets the home spaces. But if I have two functors like this, so that f is left adjoint to g, then remember that we had a natural transformation from fg to the identity here of d, and we have a map from the identity of c to gf, and these were not, neither was isomorphic, not necessarily an isomorphism, but what we could do is compose, say for example, grab this. Did I do that correctly? G is a map from D to C, well, a functor, and then F sends it back to D. Yeah, so that's correct. Okay, so what you could do is this guy is an endofunctor of C. And you can apply f. You can compose this functor with f to get a functor from C to D. And you can compose this guy with f to get a functor from C to D. So you always have a morphism of functors between f and fgf. The category of functor was a category, so composition is associative. So fgf is the same thing as fg composed with f. So I don't need to write parentheses here. So I always have this, which is f composed with this adjunction. And I always have the following here. I can compose with g this side. So I always have from g to g composed with f composed with g. This is just g composed with this adjunction here. Okay, so the lemma is these two are isomorphisms. Lemma, alpha and beta are isomorphisms. So whenever you have an adjunction, you can start this thing of, you can play this game of like trying to get more adjunctions, but you're not going to get more. So this thing is idempotent. So again, if you compose this thing now with G again, you're going to get an isomorphism from GF to GF, GF, which is just essentially the identity of GF. Okay, so let's prove this. So the first, these two might not be isomorphisms, but this guy is. I'm sorry, this is not what I want to prove, and this is actually clearly false. What did I say? No, this is fine. As it is fine, but I want to prove something stronger. So I want to do the following. So we can grab f, we can map it to alpha to fgf. I think I don't and no one is stopping me, so I guess you guys are. So this was clear what it was. It was applying f to this. But this doesn't make any sense. The arrow here goes in the other direction. Applying g on this side and g on this side, I will get a map this way to g. Now this makes sense. So now let me state what the lemma is. Now that I have these two, what I can do is, let's look at G composed with F, and now via alpha, and then G goes to G, F, G, F, which is the same thing as G, F, G composed with F, and via beta, this goes to G composed with F. And this composition is the identity. So that's the lemma. Okay, so let's remember how we constructed alpha and beta. Okay, so what we did is we looked at f alpha, f of a, and we had the identity of f of a here. And this was isomorphic because of f, because of the adjunction to hom a, g, f, a. So the image of the identity of alpha here by this isomorphism is what we're calling alpha of a. So that's this alpha here that maps from the identity. No, I'm sorry, this is what we're calling beta. This is the guy that maps from the identity of C to GF of C. And the same thing for hom GB, GB. We had the identity on B here, and this maps to hom FG B, B, and this is what we're calling alpha of B. Okay, but now what we could do is let's grab this guy and let's take F to be of, let's take B to be of the form F of A. Now this is going to go to hom F, G, F, A to F, A. And this is this map beta. Okay, so this is this I am abusing notation and calling this beta in the same way as this beta here. But if you notice, what am I doing this? I think I'm mixing F with I think I'm calling alpha and beta both things in a different way. So, holy crap. So this I composed with F and I got this. I think this is what I'm calling now beta, and this is what I'm, yeah. So I'm mixing both betas and alphas. So we have these two adjunctions, and I think I'm mixing what I'm calling beta and what I'm calling alpha. Whatever I call this guy, I wanted to call it alpha, and whatever I call this guy, I wanted to call it beta so that it coincides there. But then this thing here is no longer alpha, this is beta again. I apply this arrow and compose with F to get this. And this thing here is alpha again. I got this arrow here and I compose with G. Being dyslexic. So this thing here is a guy from FG to the identity, which should be called alpha, which is at least now is consistent. And this thing here is the same thing. It's FGF to F. So it's something that goes from FGF to F. Yeah, so it should have been this alpha composed with F on the other side. So what I could do is take FG and compose with F on the other side and map it to F. Okay, so this is alpha composed with F on the other side. And this thing here is, this is alpha composed with G on the other side. It gives you this map here. Okay, now it makes sense. Okay. Okay, so this image here is from FGF to F, which is this guy that I'm calling beta. No, from FGF to F, which is this guy, which is alpha F of A. Okay, so now let's check all of these compositions. So what I want is, I want to make this composition of this functor here, this isomorphism, and then compose with this guy again. Okay. So what I claim is that this is the identity map of functors. So let's apply this guy. This applies this functor to, well, let's look at the composition of all these morphisms. Okay. So let's take an object A in C. Now this map here is a map from G, F, A to G, F, G, F, A. Which you see is going to be, did I do this correctly? From GFA to GFG. Correct. So what I want is to grab. Right. So I want to grab this guy and compose it twice. So I want to look at, I want to do this twice now. Can I not do this? I'm sure I'm going to get this wrong, but anyways. So I'm going to take this A to be of the form G of B. I'm going to take this A to be of the form G of B. So this is going to be F of G of B, F, G, B. And this is hom. Now, this looks like G, B, G, F, G, B. So we have a canonical object here, which is a map from GB to GFGB. So now we can do this, play this game again, and we can just take B to be of the form FA here. FA, which has the identity guy inside. And this is isomorphic to hom. And now I can just move this F, which is left adjoint to the other side, to get a GFA to, I am moving the first F to the side, GFGF A. Okay, so this guy here, which is the image of the identity here, is this arrow here that I needed here. Holy crap. Okay. So that's the arrow that I have, the first arrow, which is the diagonal one there. Now the arrow here in this side is the one that corresponds to the same game being played now on this side. So we have one element here to FA, and now I need to do it, I need to apply it to G. I need to land in GFA. So let's take this guy here and apply it to A is equal to GB. So I'm going to have GFGB, GFGB. And I look at home. And now I move this G, which is right adjoint. Oops, no, I did something wrong. What did I do wrong? Oh, no, that's correct. So I want to move this G to an F on the other side. So I get an F, G, F, G, B to F, G, B. So I have a map from F, G, F, G, B to F, G, B, which is the image of the identity homomorphism here. And that is the map from F, G, F, G, F to G, F of something. Okay, so now the composition of these two maps correspond to just the identity object, the composition of these identity maps on these two guys, which is the identity. Holy crap. Lost too much time on the trivial part. Same as last time. Okay. The thing I want to prove is the exactness. That's the only thing that actually matters. So let's grab a functor on triangulated categories. Let's take an adjoint. So now let's take F, which is left adjoint to, let's say, G. But now this is between triangulated categories. Categories. And let's suppose that F is exact. Okay. All right, so okay, the first thing we need to prove that G commutes with translations. So I want to prove that G is exact. I need two conditions. I need that G commutes with translations, and I need to say that it sends triangles to triangles. So let's prove that G commutes with translations. Okay? So I need to find this isomorphism, but for G. So I need to prove that G composed with the translation now on D. So G is a functor from D to C. So I can first translate on D, then apply G, or I can first apply G and then translate on C. So that's what I need, this isomorphism of functors. But then an isomorphism of functors is given, therefore, by hums. So I need, what I can do is, for any object A, I can look at what is the hum from do I want to take home? Oh, I think I'm using always B. Just a second. Right. So if I want this map of functors, I need to give you, for any object of B, I need to give you a map from G, B shifted to to the shift of G B. I need to give you this isomorphism between these two guys. But to give you this isomorphism, and this I need to give you for every B, what I'm going to look at is take an object in C, and let's look at hom in the category C of A into this guy, into G of B shifted by 1. So this is the shift in the category D. Now, G is right adjoint to F. So this is the same thing as hom in the category C, and this is by adjunction to F of A into B shifted by 1. Now, shifting in the, there's something very wrong. I guess, yeah, so there's something very, very wrong here. I'm taking B's in the category D. This is what's wrong. F goes from C to D. So this is in the category D, and this is in the category C. That's fine. Okay, so now, this is the shifting in the category D. So A is always objects in C, and B's are objects in D. So shifting is this translation in D is an equivalence. And the inverse of that equivalence is the shifting, is what I defined it to be shifting by -1. So I can apply, since it's an equivalence, I can just use that equivalence. And in particular, this is the same thing as hom in the category D of applying TD inverse on this side and TD inverse on this side. Okay? So this is TD inverse of F of A, and this is TD inverse of B shifted by 1, which was TD of B. Just being anal, but this is just hom in the category of D of F of A, now shifted by -1, and here I have B. Okay, now F was exact. So F satisfies this. In particular, you can compose this with TD inverse twice, I guess. Yeah, so F is exact, so I want to claim that this is the same thing as saying that TD inverse of F is the same, is isomorphic to F composed with TC inverse. To do this, well, you grab this and compose with TC inverse on this side and with TD inverse on that side, and you're going to get F TC inverse, and here you're going to get TD inverse F. So that's this identity here. So therefore, this thing here is the same thing as hom in the category D still of F of A inverse. Now I'm shifting in C first and then applying F into B. And now again by adjunction, this is hom in the category C of A shifted now in the category C by, again, this was -1. -1 and GB. And now again, since TD, TC is an equivalence, I can apply TC on both sides. And this is hom A into GB shifted by 1 now. And these are isomorphic. Okay, so what I've gotten is that for every A in the category C and every B in the category D, I have a natural isomorphism. Well, I have an isomorphism of these hom spaces. So now you fix B, and you need a lemma varying A. So for fix B, fixed, let's do this here. I just probably don't want to remove this. So fixing B, and Yonera shows that we're getting an isomorphism between G of B shifted by 1 and G of B shifted by 1. So that means that G commutes with T, which is what we wanted to prove. So that's the first part. So now I need to check that G sends triangles to triangles. So even to make sense of this identity here, we needed the fact that the functor needed to commute with translation. So now that we have this, we can check that G sends triangles to triangles. So let's grab an exact triangle on D. So we have an exact triangle now on D. See, A shifted by 1. So this is exact, a distinguished triangle on the category D. And let's apply G to this thing. And we will want to have that this guy should be exact. Well, now we know that it doesn't matter where I shift this. So I'm going to just use that. And it doesn't matter if I take G of A shifted by 1 or G of A shifted by 1 because those are canonically isomorphic now. I fixed this isomorphism. And notice that this isomorphism actually was fixed once that I've chosen. So the only choice that we made here is here when we identified these two. Here we made a choice. We made a choice that said how we are identifying F T inverse with F T inverse here. So that choice immediately gave us how we're going to identify these two. Okay, so I want to prove that this is an exact triangle. But what I can do is in the category C, I can use TR1. So this guy is always there, this morphism. So I can always look at this. I can look at G of A, G of B, and extend this to a triangle in the category. Probably C prime is, well, it doesn't matter. I'm going to choose C prime to GA shifted by 1. So this is distinguished in C because of TR1. Right? So TR1 says that if you have a morphism, which in this case is G of this morphism, then you can always extend it to a distinguished triangle in that category. Okay. Now, what I would want is to prove that this guy is distinguished. And if I have any map from this to this, which is an isomorphism of triangles, it's going to make it distinguished. Because TR1 also said that if you have things that were isomorphic to distinguished triangles, then they had to be distinguished. So I want to have an isomorphism between this and this. How do I do that? Well, clearly I have the identity map between these two, the identity map between these two, and the identity map between these two. But that's not necessarily going to commute. And also, this is not distinguished yet. Well, anyways, let's see what we can do. What can I do? So let's see what we can actually do. Oh, I see. So now this is a distinguished triangle in the category C, and we know that F is exact. So what we know is that F of G of A to F of G of B to f of C prime to f of g of A shifted by 1, now this is distinguished in D. This is because f is exact. I want to finish this time. Okay, so f is exact, so it gave us that this guy is distinguished. Okay, so now what I can do is, let's look at taking g of this thing and use that thing that we know that that's going to map to g of A and that that's going to be an isomorphism. So let's look at taking g. So again, I have g of A into g of B into C prime into g of A shifted by 1. And I'm going to be looking at g of this, which this is the one that I'm interested in. So I have this g of A, g of B. So this starts exactly the same as that, but now I have this g of C into g of A shifted by 1. And I can put this guy in the middle. I can put g of this guy in the middle of those. So let's put this first, and then let's tell you what it is. GFG of A, GFG of B, GFG. Here's a good question. Do I want to have it of C prime or of C? GF of C prime, I think is fine. And here is GF, G of A shifted by 1. So now, this is distinguished. No, this is not distinguished yet. Sorry. Why is it? So what I had is that this guy is distinguished in D. Oops. It doesn't matter. We don't care about this guy be distinguished or not. The only one that we know is distinguished is this guy. Now, we have a map from this to this. This is just the adjunction. This, hopefully I didn't remove that guy. So we have this natural map from G to GFG. So we have this map here from here to here. And this composition here is that identity. So this is an isomorphism. We have a map from here to here, and this composition here is an isomorphism. And we have a map from here to here, and this composition here is an isomorphism. Right? So these are all these isomorphisms that we had before. Now, how about the other ones? Again, so I started with this G, which is right adjoint to F. So we always have a map from here to here for any object. And I claim that this other one comes from, I would want to have just one extra map there, or probably, right. And finally, what I have is that G of A, G of B, G of, C prime, and G of A shifted by 1. This is the distinguished triangle that we had. So we had two distinguished triangles. We had this one that we started with, and then this one that we just constructed by TR1 on C. So this was distinguished. And I claimed, so this is distinguished. Right, so this statement here was that applying F to that guy was distinguished. So this is distinguished. And we also have No. So wait. How do I construct a map? I claim that there should be a map from either C to C prime or from C prime to... I need one extra map. I cannot use TR3 because I need it to apply TR3 when I need to have them already to be distinguished. How do I get this map from F of C prime to C? So this is distinguished. Oh, I see. Okay. And this is distinguished that I started with. Now these are this is distinguished because this is F applied to a distinguished triangle, and F is exact. This is distinguished because I started with this. And F is left adjoint to G, so this map is the adjunction between FG and the identity. Now this map is the adjunction between FG and the identity. This map is the adjunction, and now I have maps between actual distinguished triangles, so therefore this map exists. So now this map is G of that map. I have a map from FC prime to C, therefore G of that map gives me a map here. All right, so now I have this row in the top, this row in the bottom, and out of these three arrows between this, and this, two of them are isomorphisms. I cannot conclude that this guy is an isomorphism because this is not, this is not yet an exact triangle. So if this was a distinguished triangle, then I would know that this is isomorphic to this. Because, well, two of those arrows are isomorphisms. But I do not know that this is a distinguished triangle yet. But we now know that those maps are naturally there, everything commutes, and we know that these maps are there, everything commutes, and these compositions are isomorphisms. So forget now about the arrow in the middle. The arrow in the middle is completely, well, yeah, it might be. So now we have those. So let's apply hom from anything into those. So let's take hom D into all of these objects that are there. So I have hom D into G of A to hom D into G of B to hom D into G of C prime. No, into C prime. Yep. And then I have hom D into G of A, hom D G of B and G of C into G of B. So these two are the same thing as this, but this guy is the interesting one, hom D into G of C. Okay. And you can extend this, well, no, let's continue. Just a second. Right. So now, this was part of an exact triangle. This by construction, this was by construction a distinguished triangle. So this I can extend on both sides to a long exact sequence of vector spaces. I can put here hom, well, whatever it is. So this is going to be D into G of C prime shifted by -1. And here I can put hom D into G of A shifted by 1. And this is exact. These are all vector spaces. Now this one I cannot say the same because this is G of C. So, and this guy here is not known to be a distinguished triangle. However, these are Homs into G of something. And G is right adjoint to F. So this is isomorphic to Hom F of D into A, Hom F of D into B, Hom F of D into C. And now this sequence is exact because A, B, C, A shifted by 1 was an exact triangle in the category C. So for any object f of d in this case, this sequence was exact. We've checked this. So now this guy can actually be extended on both sides by adding here Hom f of d, and now A shifted by 1. And then here I can add Hom f of d, and now C shifted by -1. And now apply adjunction again to get here that you could extend this to Hom d into G of C shifted by -1, and here to Hom d into G of A shifted by 1. And now we do have two sequences of vector spaces. These are exact sequences of vector spaces. And this is an isomorphism. This is just the identity. This is an this is an isomorphism. This is an isomorphism. This is an isomorphism. And this is the one that we were looking for, which by the 5 lemma is an isomorphism. So for every D, we get an isomorphism between these two Hom spaces. And this implies, therefore, that C is isomorphic to G. I'm sorry, C prime is isomorphic to G of C by Ionera again, which is what we want to prove. So once that you have that this is an isomorphism, well, this one is a triangle that is isomorphic to a distinguished triangle. Therefore, by TR1, it has to be distinguished. Okay. So we've proven that adjoints of I'm sorry for the 5 minutes. Adjoints of exact functors on triangulated categories are exact. Next time, I'm not sure if I'm going to talk about this for Serre functors. Serre functors are exact. You can check. That's not hard. But then, so I'll start looking at adjunctions and try to construct the derived category.